The sequence of prime numbers dictates an absolute deterministic structure, yet mapping their exact placement yields a distribution that mimics a continuous, two-dimensional random walk. For centuries, infinity was treated as a theological abstraction. In the late 19th century, mathematics required absolute deterministic certainty, forcing a transition where the infinite had to be measured, categorized, and subjected to rigorous proof. Geyer-Cantor proved that infinity possesses different magnitudes. Through his diagonal argument, he demonstrated that the continuous, uncountably infinite set of real numbers exists on a higher mathematical plane than the countable infinity of whole numbers or fractions. While Western mathematicians pursued strict formalism, Srinivasa Ramanujan applied a highly intuitive methodology in the early 20th century. He developed complex representations of infinite series and modular forms, directly mapping the deep, hidden architecture of numbers. Determining the ultimate structure of infinity requires a synthesis of these two approaches. We must abandon purely deterministic models and apply the mathematical mechanics of pure randomness. In 1900, David Hilbert presented 23 unresolved mathematical problems. His eighth challenge, the Riemann hypothesis, remains the most critical open question regarding the precise distribution of prime numbers. A century of standard analytic number theory has failed to yield a proof. The deterministic tools used to track individual prime coordinates break down at massive numerical scales. In 2001, mathematicians Philippe Bion, Jim Pittman, and Mark Yor published a paper mapping the deterministic Riemann z-function directly onto the mechanics of Brownian motion. The BPY synthesis demonstrates a direct equivalence. The statistical properties of random, chaotic paths perfectly mirror the analytical properties governing the prime numbers. Proving the Riemann hypothesis requires us to stop treating the primes as static coordinates and instead translate their behavior into a question of physical probability. This animated graph shows a 1D Brownian bridge. It begins at 0, wanders randomly, and strictly returns to 0. We isolate variable y, the maximum span of this bridge, which follows a Kuiper probability distribution, a statistical measure for data wrapped around a circular domain. The analytical engine driving this physical probability is the Jacobi theta function. It serves as the fundamental solution to the heat equation, mathematically governing how energy and particles physically diffuse through space over time. Because these theta functions are doubly periodic in the complex plane, their natural geometric representation forms the continuous topology of a torus. This same mathematical architecture, which dictates how heat diffuses through space, supplies the exact topology necessary to map the prime numbers. This equation represents the Mellin transform, a mathematical filter converting a physical probability density into a number-theoretic function. We input the Kuiper distribution of our Brownian range y into the integral side. The resulting output is exactly 2 times the Riemann c function. This match occurs because Bernard Riemann's original integral for the c function relies on the exact same Jacobi theta function that governs physical diffusion. Through the Mellin transform, BPY proved an absolute structural identity between the analytical placement of primes and the physical dynamics of a random walk. The strict deterministic Riemann c function is the analytical shadow cast by the stochastic reality of a Brownian excursion. In 1997, Xianjun Li reframed the Riemann hypothesis, eliminating the need to locate individual zeros on an infinite plane. He established a new criterion. The hypothesis is true if and only if a specific sequence of coefficients, lambda n, remains strictly positive for all values of n. This maps Li's Mobius transformation, warping the infinite vertical critical line into a finite unit circle. Under this mapping, the zeta function zeros manifest as red radial rays on the perimeter. They pack together with infinite density as they approach z equals 1. Li's equation successfully reduced the search for infinite abstract coordinates into a strictly binary test of sequence positivity. BPY applied their stochastic framework to Li's deterministic coefficients, bypassing the need for manual calculation. They proved that the lambda n coefficients are exactly the cumulants of a new random variable derived from the Brownian range. Cumulants are simply statistical values that describe the shape of a probability distribution. This embeds Lee's criterion strictly into probability theory, specifically relying on infinite divisibility. This is a property where a distribution can be broken down into an infinite number of identical, smaller, independent pieces. This line chart displays recent numerical verifications of the lambda n sequence. Even for massive iterations, the coefficients maintain an extreme positive value along a steep logarithmic curve. Superimposed over this smooth upward trajectory are microscopic oscillations. If the Riemann hypothesis were false, these minor oscillations would exponentially explode and drop into the negative axis. They remain consistently stable. By proving the coefficients function as stochastic cumulants, BPY turned the definitive proof of the Riemann hypothesis into a solvable question of infinite divisibility. This dual nature between number theory and probability continues to produce unexpected physical applications today. High-frequency spot volatility data in global finance fluctuates with rapid, unpredictable chaos. This exact data behavior forms a direct physical counterpart to prime distributions. The exact stochastic functionals initially developed to describe the zeta function are now implemented to calculate periods of extreme market volatility. In theoretical physics, the spacing between zeta zeros perfectly models GUE statistics. GUE, or the Gaussian unitary ensemble, is a statistical model describing the highly chaotic energy levels within complex quantum systems. The final requirement is clear: proving that the underlying random variable belongs to a specific class of self-decomposable distributions will permanently prove the Riemann hypothesis. A microscopic dust particle suspended in fluid moves entirely according to the fundamental mathematical laws of physical stochastic diffusion. The behavior of that particle operates on the exact same mathematical laws dictating the sequence of primes. At the deepest level of reality, the boundary between deterministic mathematical order and physical stochastic chaos dissolves.